Welcome to Lesson 8, Part A. We are going to present the basic risk matrix. The maximum historical drawdown. That is well known to the systematic traders. We have already defined this metric in Lesson 6. Then we have the VAR, which stands for Value at Risk. At last, we have the expected shortfall, abbreviated as ES. Let me explain something about the link between these metrics. Usually, the VAR is bigger than the maximum historical drawdown, and the expected shortfall is bigger than the VAR. When I say bigger, I mean bigger in absolute value, as they represent losses, thus they are negative figures. The illustrative figures reported on the right side are very close to those of our system combination. The VAR and the expected shortfall refer to a confidence level. Feel free to go back to Lesson 3 for a recap on this topic. The maximum historical drawdown can be thought of as the bottom peak of the underwater curve presented in Lesson 6. As regards this chart, we just focus on the right-hand side of it, and we take into account just the blue line for the time being. Here are the shortcomings of this metric. First of all, it is affected by the track record limitedness. Simulation-based metrics can overcome that. Secondly, it is affected by the order of the recorded trades. Imagine that you have two systems to compare, and they are equal in that they have a track record of just 4 trades, and the mean profit, an expected value of 0. The first one wins, then loses, and then it wins again. The second instead loses, wins, then loses, and wins again. The former has a drawdown of 20%, whereas the drawdown of the latter stands at 10%. This metric makes the former look much worse than the latter, despite the fact that they have the same profitability, 0, and the same standard deviation. Let's do the upgrade to the VAR. That is defined as the lower bound of the negative returns at a 95% confidence level, meaning that there is a 95% likelihood to get returns higher than the VAR. Look at the green arrow here. Here, we further upgrade our risk assessment, introducing the expected shortfall, abbreviated as ES. That takes into account the tail of the profit and loss distribution, meaning that we estimate the average loss that we incur in the unlucky event that the return is worse than the VAR figure. Let's take these two illustrative systems whose profit and loss distribution are drafted here. They have exactly the same VAR, but the one on the right-hand side has a bigger negative tail and then a bigger expected shortfall in absolute value. Because of that, the latter is deemed more risky than the other. Now, let's see how it is possible to reckon up these two metrics. If we assume that the profit or loss distribution be normal, we can estimate the VAR and the expected shortfall by means of closed-form solution, meaning that there is a formula for that. This formula involves the mean and the standard deviation of the profit and loss distribution, which are called parameters, and the probability density function of the normal distribution, whose table can be downloaded from the internet. This quite easy estimation method is called parametric in that it heavily relies on the assumption that the profit or loss distribution is normal. This parametric estimation of the VAR and of the expected shortfall has two shortcomings. First of all, the track record limitedness. The smaller the sample, the less reliable the estimate of the parameter, and namely of the parameter sigma. Secondly, the normality assumption for the profit and loss distribution is a wrong assumption. We have seen in lesson 1 that trading systems deliver profit and loss distributions that heavily depart from normality. This assumption is even less appropriate for the expected shortfall, as it expressly deals with the tails of the distribution. Let's recap shortly what flat tails mean. Let's see then how it is possible to estimate this stuff the right way. It is necessary to resort to simulation based on historical data. That is called non-parametric approach, in order to distinguish it from the one presented in the previous slide. This refined approach is based on numerical computation, namely on the Monte Carlo simulation, which is denoted in MASASP as MCP. Remark that also the standard deviation can be estimated by means of the Monte Carlo simulation. That is reported as SIG-MCP. Let's see how this Monte Carlo method works. This method consists of n-fold sampling from a given population distribution or from a larger sample. In this case, we create 1000 subsamples from the large sample encompassing all profits and all losses of the recorded trades. If the system generates 20 trades per year, it is just an illustrative figure, we create many subsamples of 20 trades each. Sample 1, sample 2, sample 3, and so on. After that the trades have been randomly allocated to these samples, we compute the overall return of each sample. We generate as many as 1,000 samples. At last, we plot the whole set of 1,000 annual returns related to these 1,000 samples. Then, we compute the descriptive statistics of this distribution. The fifth percentile of this distribution delivers the VAR. Besides, a proper algorithm is applied to this data in order to deliver the expected shortfall. Remark that the VAR and the expected shortfall estimation presented here still need some important refinements. These are going to be addressed in the next video. The metrics discussed in this video are reported at page 2 of the risk scorecard. Well, that's all for the time being. See you at lesson 8, part B.